Today we start our probability introduction. Let's review some definitions we've already discussed. First, we had an experiment, which was an observation of a random phenomenon. An outcome was then any result of the experiment. The set of all the outcomes put together became our sample space, and an event was any set of outcomes from an experiment. Again, let's look at an example to really clarify what those definitions mean. So, an easy example would be rolling a set of dice. The outcome would be the number of dots observed on the dice. And an event could be something like getting doubles. As we continue our definitions, we have a couple really important things. So let's first start with events that have equally likely outcomes. So this is just any type of experiment in which all outcomes have the same chance of occurring. So our first important thing today is theoretical probability of an event. This means we would look at the number of ways an event can occur divided by the number of elements in the sample space. Mostly when we look at this, the outcomes will be assumed to be equally likely. Because we're going to do this a lot as we talk about probability, I do want to show you the shortcut that we could use. We could say that the number of ways an event can occur can be the number NE. So remember, we've talked about N just stands for number, and E is the name of our event. And then in the denominator, we have N of S, so the number of elements in our sample space. This saves us from all the words that we could write, and we could just write something really short. Now, that was theoretical, where we just think about something. Our second thing that's really important today is called empirical probability. So the empirical probability of an event is the number of times an event occurred divided by the number of times the experiment was conducted. So here you should feel this action because it says the event happened, right? The experiment was conducted. So we're not just thinking about it, we're saying something really was done. So here, our probability of E is the number of times E occurred divided by the number of times the experiment was conducted. So we have what do we think will happen, theoretical, what really happened, empirical. So what's the difference? Let's try this simple question. If a woman is pregnant, what's the probability she's expecting a girl? So in our minds, when we usually think about this, we would think that the probability that someone would have a girl would be 1 out of 2. There's one way to have a girl out of the two choices of boy or girl, or male or female, right? So here's our 50-50, which comes from us just thinking in theory. Now let's check reality. So here's the CDC birth rate for Nevada for last year, and it shows you that in total there were 35,682 births, and 17,370 of those births were female. So the probability of having a girl would be 17,370 over 35,682. So let me quickly put that in the calculator. 17,370 divided by 35,682, and I get 0.4868. There's some more stuff, but let's say we stop it there. So this shows me as a fraction, then as a decimal, that we could turn into a percent that 48.68% of the births in Nevada were female. So there's a slight difference between theoretical, we thought there would be a half, and empirical, what really happened, which was 48.68%. So it's less than 1.5% different, but it is different. So let's look at some more examples. Let's find the probability of spinning this spinner and landing on a 3. So you can see I have the numbers 1, 2, 3, 4, 5, 6. They're all the same size, so they're all equally likely events. There's one way to get a 3 out of the 6 choices on the spinner. Right? So let's try that again. This time I said find the probability of getting a number less than 5. Really important that I was thinking through the words and think that less than 5 does not include 5. So it includes 1, 2, 3, and 4. So I have 4 out of 6 choices. 4 out of 6 is right, but you always want to give the best answer that you can. So anytime you can reduce the number and make it a smaller fraction, you should. So we're going to change the 4 out of 6 into 2 out of 3. So let's stay with the spinner. I'm just going to ask some more questions. So the next one I say is, well, what's the probability of getting a 4? So again, I have this one way to get a 4. out of the 6 things that are on the spinner. I like the fraction for this just because it's right. If I were to change this into a decimal, it would be repeating and I would lose something by changing it that way. So make sure you're paying attention anytime you have a homework question or a test question, quiz question, whatever. Look for, am I asking for, or the homework asking for a decimal, a fraction, or a percentage. Now the next question says, what's the probability the number is greater than 6? Well, when you look at the spinner, all of the numbers are less than 6. So this says there are 0 ways out of the 6 choices to get a number greater than 6, so I want to say the answer is 0. Then it says, what's the probability of getting an odd number? So the odd numbers would be 1, 3, and 5. So I have 3 out of the 6 choices. And remember, we said we always want to reduce if we can, so that reduces to half. Let's do 2 more on this spinner. Let's say, what's the probability we get a number less than 10? Well, when I look, 1, 2, 3, 4, 5, 6, those are all less than 10. So all 6 of the 6 choices were less than 10. Let's simplify that down to 1. So if I were to get 1, I write 1. Just like when I got 0, I wrote 0. The last one says red or blue. So the 1 is a red, the 5 is blue. So red or blue says there were 2 out of the 6, which is 1 over 3. So let's sum up a little bit of what we just did. We just actually covered probability rules without being taught them. So we can break these down, that the probability of an event that cannot occur is 0. The probability that an event from the sample space will occur is 1. And then the probability of an event E is greater than or equal to 0 and less than or equal to 1. So this shows me I can never have anything more than 100% likely. I can never have anything less than 0% likely, but everything should fall between 0 or up to 1. Finally, the sum of the probabilities in a sample space should be 1. That one we need to take a look at, so let's do another example. So say that we have this. I have 2 green, 3 yellow, 1 blue, 1 pink, 1 purple, and 1 red jelly bean. We want to fill in the chart with the probability of selecting a jelly bean at random. First thing I want to do is think, well, what is that? If I have 2 plus 3 plus 1 plus 1 plus 1 plus 1, that's 9. And you could just count them, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 jelly beans. It says 2 of them are green, so the probability of green would be 2 over 9. Let's see if I can make that a little better. All right. Then the next one says, what's the probability of getting yellow? So I can see there are 3 yellows, so I'm going to write 3 over 9. Now this one's important. 3 over 9 I can reduce, so I want to make that equal to 1 over 3. Then I said red. Well, there's 1 red. That gives me 1 over 9. Blue, there's 1 blue, so there's 1 over 9. 1 pink, so 1 over 9. And then lastly, 1 purple, 1 over 9. The only one that reduced was the 3 over 9 became 1/3, but I want you to see if I were to add up these probabilities, 2 plus 3 plus 1 plus 1 plus 1 plus 1, I would have 9 over 9, which is 1. So that's what I meant in the last one that said the sum of the outcomes, so the sum of the probabilities of the outcome of the experiment should add up to 1. This is exactly what we're talking about. All right. So here's another example. This is a make-believe class, and the grade distribution for this class had 30 A's, 18 B's, 15 C's, 9 D's, and 18 F's. I want you to use this chart to figure out what's the probability of getting an A, and then the probability of not getting an A, the probability of getting an F, and then not getting an F. So the number one thing I need to do is add up 30, 18, 15, 9, and 18. That gives me a total. Oops, I hit the wrong button. That gives me a total of 90. Okay, I can write total in there. All right, now we know our total, we can start doing the probabilities. So A, there were 30 A's out of the 90 students in the class, which we can reduce down to 1 over 3. What I want you to start thinking about is not A. So I know that 30 people in the class made an A. There were 90 people altogether. If I do 90 minus 30, that would be 60. Of the 90 people did not get an A, which is 2 over 3. What I did was try to save myself some time, right? Try not to do more work than I have to. So there's no reason for me to go back and to add up all the little pieces. I don't have to add up 18 and 15 and 9 and 18 to get 60. I can say if 30 got an A, 60 did not. So that's the same thing I'm going to think about when I go to the F's. When I look at F, there are 18 people that got an F over the 90 people that were in the class. It's important that you're good with your calculators, especially if you're not good at doing fractions and doing reduced fractions. So if you wanted to, you could put 18 over 90 in your calculator and it says 0.2. Then you should have a button, it probably looks like an F with an arrow to a D, that will change a decimal into a fraction and you could get 1/5. Just things that'll make things simpler for you. So here I have 1/5 for the probability of getting an F. So not an F, well, if 18 people got an F, the rest of the people did not. So you could do 90 minus 18, which is 72 over 50. And then again, I just said 50, but it's really 90, isn't it? As soon as I said it, I heard myself because I can't have that. That would be too high. So 72 over 90, which becomes 0.8, but then when you hit your button to make it go back to a fraction, you get 4 over 5. Okay. So again, we covered some material without really getting there. So let's review what we just learned. Not E is referred to as the complement of E. You can write not E, or you can use the notation E with a little like apostrophe by it. I would say E prime or E complement. This is exactly like what we did when we talked about set theory. It was A and A complement. So A complement was not what was in A. E complement is what is not E. The two things together always add up to 1. So if you look back, we had the 1/3 and 2/3, that makes 1. We had the 1/5 and 4/5, that makes 1. So you have the choices, either get an A or you don't. Either you get an F or you don't. That's what we're saying here with the complement rule. It's often helpful to figure out the probability of E and then subtract it from 1 to get the probability of E complement. So look for that to happen again as we talk about things in this chapter. Also notice that words at least will end up feeling like the complement rule. So let's just further our talk and look at a bigger chart. So this one breaks down a group of students who are polled about their majors, and the results are in the table. We're going to use the information to find the probabilities. So in the table, we have 45 business majors, 15 nursing majors, 20 engineering majors, 50 liberal art majors, 35 other majors, which gave me a total of 165 students. All right, so the probability of business, I can see there are 45 business majors out of the 165 students. When you put that in your calculator, let's say we do 4 decimal places, so I get 0.2727, which we could also call 27.27%. Then let's look at not liberal arts majors. You can see there are 50 liberal arts majors, which means 165 minus 50 is 115 students that are not liberal arts majors. 115 over 165 gives you a 0.6969 for 4 decimal places, but we don't want to stop there. I really need to look at the 5th decimal place to decide what happens. This 6 being greater than 5 says I need to round up. When I round the 9 up, it makes it a 0 and makes that next 6 a 7. So I end up with 0.6970, which is 69.70%. Let's also look at the probability that a student's an engineering major. So I can see 20 out of 165 gives me a repeating 0.1212. So I have 0.1212 or 12.12%. And then the last one says nursing or other. So nursing is 15, other is 35, 15 plus 35 over 165. So start with your 15 plus 35 is 50 over 165 gives you a 0.3030 or 30.30%. If you do or don't write that last zero, it doesn't matter. All right, so then I thought, let's just look at a table and do it a little bit different way. So these are the ages and citizenship of the Golden Knights hockey team from the fall of 2019 data. So here's what I have. I have categories of Canadian, US, and other. I have age categories of less than 24, 24 to 29, and over 30. Number one, what's missing in every way are totals. So I'm going to put totals both on the right and on the bottom. So my total number of players under 24 would be 3. The total number of players 24 to 29 would be 12. And then the total over 30 is 6. Same thing across. If I look at the total number of Canadians, I had 15. Total number of US, I had 4. And then other was 2. What should happen is if I add the numbers in the vertical column, 15, 4, and 2, that gives me 21. Also, if I add 3, 12, and 6, I get 21. So that's kind of a double check to make sure you have the right data. All right, so the first question I asked is, what's the probability the person is 30 or over? So I can see there are 6 players. Out of the 21, that would be 30 and over. 6 is a multiple of 3, so it's 21, so I know I can reduce this to get 2 over 7. The second question says, what's the probability the person's not a U.S. citizen? So when you look, there are 4 U.S. citizens, which means there are 17 that are not, out of the 21. You could also have added Canadian, 15, and other 2. That would give you 17. 17 over 21 I can't reduce, so I just say I'm done. Same thing, let's go a little farther. And remember, I had my sums here, so let's just write them in again because I switched the page. Remember, that was 21. Okay, so this one says, what's the probability of the players from 24 up to 29? So I had 12 out of the 21. 12 and 21, again, both multiples of 3, so I divide by 3, I get 4 over 7. Then this last question about the Golden Knights said, what if the player is Canadian or between 24 and 29? So Canadian is the 2, the 8, and the 5. And then between 24 to 29, I have the 2 and the 2. So I have 2, 8, 5, that's 15, 16, 17, 18, 19 of the 21 players. It's important there that you don't double count something, right? Don't go across and down and add the 15 and 12 and get 27 because we don't have 27 players. So you want to make sure that you're not double counting anybody when you get to a chart. So this part, we're going to review rolling a die and just think again about the difference between theoretical and empirical. So if you just think for a minute before we read all of this about rolling a dice, I should have the same probability of getting a 6 or a 4 or a 5 or any of the numbers on the die. That shows you it's a fair die. But there's a difference between actually doing the experiment and thinking about it. So I said, well, what if I had rolled the die 10 times and I got this result? So I got a 1 twice, I got a 2 twice, I got a 3 one time, a 4 one time, a 5 one time, and a 6 3 times. So I used a generator that came up with these things because I have it on my calculator, so it'll make this experiment for me. So based on this experiment of rolling the die 6 times, or 10 times, sorry, I can see that I got a 6 3 times, so 3 out of 10 is 30%. A 4 I only got once, this says 1 out of 10 is 10%. Now, theoretically thinking, I think the probability should be the same. But what happened in real life was that they were different. So I want to say, well, what if I did it more? What if instead of doing 10 times, I added another 50 times to this experiment? So I did. I had my calculator do it 50 more times and tally the results. So now in this new bigger experiment, I have a 1 13 times, a 2 8 times, a 3 6 times, a 4 8 times, a 5 11 times, and then a 6 14 times. And remember, there's a total of 60. So now when I look at the probability of getting a 6, I had 14 over 60, which is 23%. And then the 4, I had 8 times now over 60, which is 13%. Again, they're not the same, but they're closer than before. In the first experiment where I did it 10 times, it was 30 to 10. Here it's 23 to 13, so I can see the gap is shortening. So what happens is the more times the die is rolled, the more even the results will become. So this is something we call Bernoulli's law of large numbers. An experiment needs to be repeated a large number of times to arrive at the event's probability. This is like our dice experiment. We roll a dice a few times to get a probability of 6, but we really need to repeat the experiment a large number of times to find the true probability. In many experiments, we don't know what the real probability of an event will be. So what does that mean? Consider a new medication. Scientists don't know the result of giving a patient a new drug until the drug has been tested. Tested on a few people would not be adequate to predict the results of the drug. They need a large sample of people to be able to accurately report the result of the drug. So I grabbed one. This is a Prilosec study that you can see the clinical trial experience with Prilosec monotherapy. And what you can tell if you were to read through this, that there were 3,096 patients, a big number. And this is important that when new drugs are introduced, we want it to be done for a lot of people over a large number of time because we want to see what happens in the long run. So we want diversity in the background. We don't want it to be on all women or all men. We don't want everyone to be a child or everyone to be an adult. We want it to be a reflection of the people that will later take the medicine. So let's try again. I'm going to give you a couple, and you know what I always say, try them, pause the tape, come back, see how you did. So this is a survey of 500 people revealed the number of dogs they owned. A person selected at random. Let's find the probability that the person doesn't have a dog, has just one dog, or has less than 3. So pause me, try it, then come back. All right, so let's start with the person does not have a dog. We can see there are 320 people that don't have a dog. Of the 500 people that I told you were surveyed, 320 over 500 is 16 over 25 if we reduce it to a smaller fraction, or 64% if you change it to a decimal and then decimal to a percent. So same thing, exactly one dog, I can see 125. So I do 125 over 500, which is 1/4, which is easily 25%. The last one says less than 3. So less than 3, you could add 320, 125, and 40, and that would give you 485. Or you could say 3 or more was 15, do 500 minus 15. Either way, you get the same number. 45 over 500 says 97% of those surveyed had less than 3, right? They didn't have more than 3. So less than 3 dogs was 97%. All right. So the last thing we're going to look at is rolling 2 dice. So this becomes a little bigger. For clarity, I made one of them red and one of them white, and then I put the white in black numbers because you can see that. So I guess I could have made them red and black so that you can tell that what the first number is and the second number. Notice there are 36 outcomes. 6 choices for the first die, 6 choices for the second. When we multiply that together, that gives us 36 choices altogether. So let's try this. Let's find the probability that both of the numbers are even. So we want to look through all of these 36 choices and look at when were both of the numbers even. This gets a little easier because I know like this first column that starts with 1, don't have to look at it. 1 is odd, don't care. So the 2, I can see 2, 2, 2, 4, and 2, 6 are even. I skip the 3s because 3 is odd. But then 4, 2, 4, 4, and 4, 6 are even. Again, skip 5, so I can say 6, 2, 6, 4, and 6, 6 are both even. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of my 36, which is 1/4. So there's my probability both numbers are even. What about getting 3? So it doesn't say 2 3s, it just says a 3. So I could have 2 or I could have 1. So as I look down the first column, the 1, 1, 1, 2, I can see I have 1 3. Then the 2s, I have 2 3. Then that 3 column, I have all of them. So I'm going to circle everything in that third column. From the 4s, I circle 4 3. From the 5s, 5 3. And from the 6s, 6 3. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 36. 11 is prime, it doesn't reduce, so we say that's our answer. Now, this is nice because the next question says, what's the probability of not getting a 3? That'll just be the opposite. So using the complement rule, I say 36 minus 11 is 25. So 25 over 36 is the probability of not getting a 3. How about the sum is 4? So with the sum, I'm looking at when I roll the dice, think like playing craps, we're looking at what happens when I put the numbers together. There's a lot of symmetry in this graph or this chart, so I'll show you it as we go. So look, I have 1, 1, that's 2. 2, 1 is 3. 3, 1 is 4. Let's circle it. 4, 1 is 5, so I'm done. Next column, 1, 2, that's 3. 2, 2 is 4. Once I hit the number, I'm done. I go to the next column, 1, 3, that's 4, and I'm done. After that, 4, 5, 6, those are already too big. So I have 1, 2, 3 out of the 36, which I can make 1 over 12. Do you notice that the 1/3, the 2, 2, and the 3, 1 form a vertical? All the verticals in this chart will have the same sum. So if I went to the middle, 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1, they all add up to 7. So when I'm looking at diagonals, I always have that equal sum, which makes our life easier when we're trying to answer questions. The next question says the sum is greater than 10. So greater than 10 means it could be 11 or it could be 12. I stop there because as big as it can get is 6, 6, which is 12. So I'm starting at this bottom corner this time of the chart. If I move up on the diagonal, I have 6, 5, and 5, 6. That adds up to 11. And I'm really done now because the next diagonal will be 10, 4, 6, 5, 5, 6, 4. So I have 1, 2, 3, which is 3, out of 36. Again, 1 over 12, that the probability that the sum of the dice will be greater than 10.